And okay, so yeah, maybe I will stop my video. I think it will be better for the connection. And yeah, so I'm gonna talk about the topic which was presented by Jarek recently, a few weeks ago. So this will be very connected with his talk. But don't worry if you don't remember that or you missed the talk. I'm gonna remember everything from the beginning, or at least the parts which will be important for this presentation. So to start with, let's think about the brain as a collection of brain regions, and more precisely, think about the cortex as a collection of brain regions. So in the projects we were working on, we were considering 66 brain regions, and for any subject, you can build the information about the connectivity structure between these brain regions. So you can think about that as something which tells you how well the information is exchanged between different brain regions, and you can provide this information in the form of the graph, which you can see on the left. So the dark color here means that there's a good connections between between the given pair of brain regions, and the light color means that the connection is not so well. So the information maybe is not so well exchanged. And of course, you can build this connectivity information for each subject. So for each subject, you will get different connectivity information. And what is important here is that you can also describe this information in the equivalent form by using the matrix, something which is called adjacency matrix. How you can do that? It's enough to put the you can actually you have so here in the graph representation, each node represent the brain region, and edge represent the connection, and you also have a numbers representing the edges. So you can simply provide these numbers in a symmetric position in the matrix, and as a result you will build the symmetric matrix, as you can see here on the right. And once again, you can do this for each subject. So at the end of the day, you get n matrices. And for the purpose of this project, what was important for us was just the population matrix, which stores the general information about the connectivity pattern. So we just what we did, we just took the entry-wise average, and we treat the resulting matrix as an adjacency matrix for the whole population. So summarizing, you have one matrix for whole population which tells you about some average connectivity pattern. And you can think, and we will use the capital A to denote this matrix. Okay. But the connectivity information I talked about is something for us as like additional information. The most primary kind of information is information about the thickness of those brain regions. So for any of those 66 brain regions, you can measure the average cortical thickness. And once again, you can do this for any subject. So consequently, when you stack this observation in the matrix capital Z, you'll have n by 66 matrix Z. Okay, so this is the matrix once again which stores the thickness, the average thickness for each brain region and for each subject. And you have some response variable y, continuous response variable, and in our situation, this was the scores from the neuropsychological test, which which were treated by us as something which is linked with the progression of HIV disease. So the larger is the entry, the larger is the value of Y, then the HIV is more progressed. You can think about this from this perspective. So pretty much you just want to think about that as something which illustrates the disease, the given disease. And B, the vector B here, this is just the object of interest. We want to estimate 66-dimensional vector, which tells us about the association between the thickness of each of the brain region and the response variable. So later, of course, we would like to select the most important brain regions in the sense that the brain regions which are response relevant, which will tell us how the structure of the brain changes while the disease is progressing. Here we also have X matrix, capital X, with its coefficients beta, and here we store some demographic data like information about age and gender and so on, and also intercept can be kept here as a first column. Okay, and also we assume the Gaussian case here, epsilon is assumed to have a normal distribution with some unknown sigma square. Okay, and now is the place where the additional information comes. I mean, we would like to think about this information about the connectivities as something which tells us, also shows us the structure of the coefficients which we would like to find. So again, in this multiple linear regression model, there is no notion of connectivity matrix yet, but we will use it in the estimation step. So for now, I just would like to say that we want to think about this connectivity information, which is represented by the capital A matrix, adjacency matrix for the whole population, as additional knowledge, which we will use in the estimation step. And this was something which was actually described by Jarek, also this way of thinking previously. So what we would like to do, we want to think about the optimization problem, which has two terms. First is the model fit term, and since we assume the Gaussian case, then we will just use the residual sum of square as something which tells us about the model fit. And the second term is a penalty. Here the function g, and we would like to build this penalty based on the additional information. So about this information about the connectivities. And we also have a regularization parameter lambda, which of course we would like to select somehow. And g is also important, the penalty term, the function. We also don't know it and have to select it somehow. So to choose the penalty, we would like to obtain the property that the stronger brain regions I and J are connected, based of course on this connectivity matrix. Then the closer coefficients, estimated coefficient, are to each other. So this is the main assumption we want to somehow reflect in the estimation procedure. So to do so, we just need to, one approach is to use is to penalize the differences between coefficients and use the weights coming from the adjacency matrix to tell how much those differences should be penalized for each pair. Okay, so when you stick to this kind of penalty, you will have the tendency exactly which you want. I mean, the larger is the coefficient here, so the larger is the stronger is the connection between brain regions I and J, then the stronger you are penalizing the difference between this coefficient. So there will be the tendency that the resulting coefficient will be closer to each other. Okay, And it turns out, and this was very helpful for us, that you can just equivalently, oh, actually, you can describe that as in the nice matrix form. So the whole summation here, you can just write as a B transpose QB, where Q here is the Laplacian of A, and Laplacian is very easily derived from the matrix. So it's just like 2 lines, and it's not problem with it. Okay. So when you put it to your optimization problem, you will get something like here, and which is a very nice objective function, and of course we still don't know lambda parameter, and this is something I would like to discuss now. How should we select it? So it turns out that this optimization problem, which you can see here, is in some sense equivalent with linear mixed model formulation. So if you assume the linear mixed model formulation, y equal capital Z B plus X beta plus epsilon, as you can see here, where vector B is a random effect vector and beta is fixed effect vector. And also when you assume some distribution on B, and in this distribution you need to use the inverse of Q matrix, then it turns out that you have equivalence with the optimization problem, which you can see on the top of the slide. How this equivalence may be described? So when I said equivalence, I mean that when you think about this linear mixed model formulation and you want to find this the best unbiased prediction and the best unbiased estimator for B and beta, you will get exactly the optimization problem of this form to find those estimates, where lambda will be given by the ratio sigma square divided by sigma b square. So these are the parameters from the assumed distribution on epsilon and B here. Okay. Of course, they are unknown, but linear mixed model general theory gives you the tools to estimate those parameters. And this brings the idea of choosing lambda, the optimal lambda. So you want to jump to the world of linear mixed model. You want to estimate those parameters first, and then you can just describe. You can just choose the optimal lambda as a ratio. You can just define it as a ratio of those two parameters. So this is the idea. Define the optimal lambda as a ratio. And the problem here is that Laplacian is unfortunately not invertible matrix, and this is required for the computation, as you can see here, because even in the linear mixed model formulation, it's assumed that the variance covariance of B is given by the some scalar times Q minus 1. So you need to assume that Q is invertible, which is not the case when you use only the Laplacian of A. So this was the one sort of problem, one problem actually we were struggling with. And last time Jarek described how this problem can be addressed, but I would like to discuss I would like to actually tell something about the different kind of the problems, and later in a few slides I will introduce the approach which can solve those two problems. So which can solve this non-singularity, I mean there's the non-invertibility problem, and also the problem which is described in this slide. So generally there is no like the best way of defining the connectivity information. You can use the structural connectivity, functional connectivity, and those two rows will give you totally different connectivity matrices. For example, structural connectivity will give you more sparse, will give you sparse matrix with positive entries, and functional connectivity generates very dense matrices, and both values, negative and positive, are possible here. Yes, so I can see that there is a question. Is Laplacian non-negative definite? Yes, that's correct. So you have well, I mean, it's the Laplacian is positive semi-definite matrix. Okay, so it's not yeah. So it's sorry, yeah, you're right. So it's positive semi-definite matrix. So you always have 0 as a singular value. So you cannot invert it. It's not non-negative, but it's positive semi-definite. It's not positive definite. Okay. Yeah, so you have 2 types of connectivity information, at least. I mean, more of them is popular. You can also think about trying something completely different. You can think about, for example, define your connectivity information based on the location of the brain region. So, for example, you want to penalize more brain regions which are localized closer to each other, like physical location. So yeah, it also has a nice interpretation, and yeah, it's intuitively should give you maybe something better, the better accuracy. And at least it presents somehow of the additional information which you would like to use. So how can you select the best option? This is the question. This was the problem, and the problem which is slightly connected with it is also the situation when you would like to split your connectivity information, because as I mentioned at the beginning, you have the whole information is stored in 66 by 66 matrix, which represents the whole network. And the brain is divided in lobes. So you have, for example, you have five lobes, as you can see here. And what should you do if you want to use this information separately, for example, for different lobes? So you have a chance to suppose that only the information for the frontal lobe is important. So you would like to have a tool for neglecting this additional information for other lobes, because this information might be, for example, incorrect. So you would like to have more flexible criteria for selecting your estimate for your optimization procedure. And how can you do that? So we would like to divide this adjacency matrix into some sub matrices. Here is exactly the division which corresponds to the previous plot. So it corresponds to those 5 lobes in the brain. So you have some blocks in your matrix. Okay, I have another question. Would it be possible to combine different connectivity matrices? Yes, exactly. This is the direction I'm going to. So, I'll try to answer this question soon. Yes. It is possible, but yeah, this is the short question. This is the short answer, and I will expand it in a while. Yeah, but coming back to this slide. Yeah, of course you can divide your matrix into 6 parts. You have the blocks, and everything else outside blocks you can think of that as a sixth part, for example. Okay, so this is what you are doing. You are splitting your matrix into 6 pieces. And you can call them A sub 1 to A sub 6. And you can define actually 6 Laplacian matrices based on them. So this this actually builds the problem that suppose that you have m positive semi-definite matrices q sub I, so q sub I when I is from 1 to m, and these are considered as potential candidates for the penalty. So maybe you don't want to choose the best one. Maybe you want to combine this information. So maybe you would like to merge the important information from each of the from all of those matrices. This would be the best if you can achieve something like that, actually, because in the reality you have no idea which if the information you are providing is 100% correct or not. In truth, it's you can expect that you won't have 100% correctness. Of course, you won't have. So you will have some false false discoveries in terms of the edges which you think of as being important. Okay, and another question. QI is used for penalizing only betas from a given region. So this is something which I will show the model in a while, and I hope this will answer this question. Yes, actually, I would assume that the whole linear combination of the quadratic forms, it's something which is used for generating the signal. So if you really use the block diagonal matrices, this will be reduced to that. So this will correspond to generating a different part of B from a different matrix. But here you don't have an assumption about that those matrices are of that form, as you can see, as you saw before. Okay, you don't have any assumption that those matrices are, for example, just the blocks of the larger matrix. You can think about them as any positive semi-definite matrices. So in particular, you can think about them as different Laplacians for example, for different connectivity measures. So one represents structural connectivity information, and the second one may represent the functional connectivity information, and for example, the third one may be just set as identity matrix, because you also want to have a chance to go in the direction of reach. Okay. Yeah, I didn't mention that, but I will do. But maybe this is the right time for do this now. That if you, instead of putting some, okay, maybe if you define Q as identity matrix and you set it here in this optimization problem, this criteria would reduce to reach. Okay, you will have just the sum of squares as a penalty here. So the reach optimization is a particular case. It's some case of this problem. Okay. So the idea is to consider the optimization problem where you have m parts in your penalty, and each of this part is has its own lambda sub I. So you have a B transpose Q sub I B, and the parameter lambda is set here. Of course, you have to select these parameters, and now it's more difficult because you have m parameters to select. But it turns out that you can do that using exactly the same idea as before, because you can also find the equivalent linear mixed model formulation. And now this time you have a more complex variance covariance matrix where you have m parameters, But once you estimate those parameters and once you estimate the sigma square from the epsilon here, you can once again define your lambdas, your optimal lambdas based on those estimated parameters. Here, please don't be confused because you have a product here and it was ratio before, but last time this the parameter was before the inverse. Okay, I said it before inverse because I could do so, and this time I'm considering those parameters inside the inverse. So you have a linear combination, but this is inside the inverse. So that's why if you had, for example, only m equal 1, then you can take the inverse of the scalar omega, and this would reduce to the ratio. So this is exactly the same as before. This reduces to the previous linear mixed model formulation for the case with m equal 1. Okay. So you can select those parameters, you can select lambdas, you can, of course, you can solve this optimization problem. I didn't mention that, but here the most important problem and the most challenging problem is the selection of tuning parameters. Once you have that, solving this problem is easy because it has an analytical solution. You don't need to use numerical solvers to find the solution. Yeah, but of course the information about the optimal lambda is crucial here. You need to find them, you need to select them somehow, and this is why you need this the step with considering linear mixed model here. So I like to think about that we are just only jumping to this linear mixed model world just for a while, just for taking the information about those optimal lambdas, and then we can just come back to our optimization problem and forget about the linear mixed model. Well, I like that way of thinking because I was working with optimizations, convex optimization problem for a while, so this is something I know well, and that's why I want to think about this, picking lambda strategy from this perspective. But of course, also you can probably focus on the linear mixed model, maybe more. Okay, and what is also important is that the non-invertibility problem here is also addressed. As I suggested before, one of the matrices you can define as identity, which is of course invertible, and it's enough that for that omega for the identity will be chosen as positive, then the whole matrix will be positive definite, because this is the sum of positive semi-definite matrices. Okay, the linear combination, and it's enough that one from this matrix is positive definite, then the whole sum will be positive definite as well. Okay, so this would, in practice, this would solve the problem of non-invertibility. Okay, so you just have solutions for both kinds of problems. You can use different information. You can handle the non-invertibility, and by the opportunity to using different matrices, you can also split your the whole connectivity information into sub-matrices, into blocks, as I showed before. So yeah, so this looks like a very general direction of yeah, of the research and of the extensions, maybe of the initial criteria. And of course, for m equal 2, and when you, so suppose that you have only one matrix, one adjacency matrix, and you can define the Laplacian, which is Q1 for now, and Q2, let's say, is defined as an identity matrix. Then the penalty becomes something like that. You have a graph part, you have a rich part here, and the whole method then reduces to Reaper, which was introduced by Jarek a few weeks ago. So yeah, so indeed this is the generalization of Reaper. Okay, so yeah, so this is I mean this was the theoretical part. What we did so far, we implemented this criteria in MATLAB. So we built actually the script, our implementation from the ground up, and this implementation lets you to fit even I tried even fitting maybe like 10 parameters, and it worked pretty fast. I didn't try maybe using very large matrices, but with the matrices from the applications we are working on, this numerical software we built worked pretty well. This is something I checked. And I would like to show some simulations, but before I do so, I have to explain the notations, which you will see. I mean, explain the graph you will see. So first, I would like to compare two methods, reach. So this is just the method which doesn't assume any additional information. Okay, so you are using just the sum of squares in the penalty, and Reaper, where you have for just one matrix for the whole population. And I think that maybe Jarek showed this graph last time, but I'm not sure about that. This graph looks like that. For reach, here on the y-axis you have estimation error. So the smaller the better. This is reach, and here on the x-axis represents the dissimilarity between A true and A observed. So A observed is something which you are using in the estimation procedure, and A true is a which was used to generate the signal. So you assume that since you don't have a perfect knowledge, some of the connections are false, and you just have a part of the true information which you have in your A observed, and A true is different, a little bit different from A observed. How different it is? Well, at the beginning of the axis, so close to 0 here, those two matrices are exactly the same, and here we were changing some connections in the way I will present in the next slide. We were mixing them and pretty much providing some garbage information, and it turns out that at some point, yeah, of course, reach doesn't care about that. It doesn't care about the additional information because it doesn't use it in the estimation, but Reaper cares about it, and at the beginning it benefits a lot from this additional information because it contains a lot of truth. Later it still benefits, but this gap is smaller, and there's some point where we are almost at the same level as Reaper, because in this moment what happened, the additional information we are providing was neglected. Because the corresponding weight, so corresponding lambda for the graph information was set very small compared to other lambda for reach. So this method has a chance, is able actually to neglect some information. So if the data suggests that the additional information you are providing is incorrect, the method may decide to not using it, and it may just go in the direction of reach. So we think about that as a very nice property of the methodology we were working on. Okay, and the dissimilarity between A observed and A true is based. This is the measure which is based on the on this simulation scheme. So this is the adjacency matrix which was used for generating the true signal in simulations, and we rewired the graph corresponding to this matrix, which means that we destroyed some connections, we added some other connections, and as a result we built the matrix which we assume that is known for the estimation purpose. And we use only this observed, so this rewired matrix for the estimation. Okay. So this is general the simulation scheme which we used. So how can we do something similar for the multiple sources? Because this is the direction I was going. Okay, so suppose that we have two matrices, and in the simulation we assume the block structure. So in capital A sub1 matrix, you have 3 blocks, and the same for the second matrix, but those blocks are not overlapping. They are, this is from a different sub matrices. And you can, what else? What's the second step of building the matrix for signal generation? So we we consider the parameter RT, the probability that the entry of the final adjacency matrix come from the first one. Okay, so for example, this is the first matrix. This is the second matrix. We wanted to have something like so. So the entries of the first one are represented by the round brackets. Here you can see square brackets. So the first step of mixing those two matrices was to build something like that. So some entries comes from the first one, the other one comes from the second one, and the probability that they will come from the first one is represented by these parameters RT. Okay, this is the first step. And the second step, now we rewired the matrix, because after something like that, you get block diagonal matrix, and of course we can rewire it. So once again, to provide more garbage information, and depending on the level of rewiring, you can have something which is more or less similar to the block diagonal structure, as you can see here. So the larger level of rewiring which destroyed this block structure. Why we did so? Because once again, we would like to use this final matrix, which you can see on the right, to build the signal, the true signal, the true B for the simulation. Then we build the observation, the response variable based on the true signal. But in the estimation process, we assume that we have those matrices, A1 and A2. Okay, these are the matrices we know. These are the pieces of information we know. We want to use them together to get better accuracy, estimation accuracy, compared to the situation where we used only one of them, or compared to the situation where we are not using any of them and we are just picking the rich estimate. And yeah, it turns out that it works. It works pretty well, at least for this simulation settings. So what happens here? Maybe I'll describe these plots. So once again, the x-axis represents the level of rewiring. So how much we destroyed this. I'm sorry. This is for the fixed rewiring level. Okay, here is for rewiring level 0, and here is for 0.3. Okay, so this situation from the left, this represents actually the middle matrix here. So the perfect block diagonal without any rewiring here edges. And this matrix on the right, this represents some rewiring level. So you can say that you have something like here. Okay, and okay. And on the x-axis, you have the probability of selecting elements from the first matrix. So at the beginning of the path here, at the beginning, you are selecting almost only the second matrix, okay, because you have small parameter RT, so you have a small probability that you will select entries from the first matrix. At the end, as a result, you have something which is very close to the second matrix. And of course, it's very natural then that by using the information coming from the around the first, okay, yeah, this Reaper, okay, this is this small confusion. This Reaper one is something which uses only the second matrix, and Reaper 2 uses only the first matrix. Sorry for that. So you can see now that the Reaper 1, which uses only the second matrix, doing pretty well, okay, because the true signal is based on the second matrix, so it's doing pretty well. The red one here is low. Reaper 2, which was built only on the first matrix, has some accuracy error, so it's not doing so well. And Aimer here, we called still MSPR, it was the first name for our first name for the method. It's selecting is going in the direction of the better one of those two choices. Okay, so it's neglecting the part of the information, the wrong information, and it's using only the information which is more correct. So it's using only the second one. Okay, and it changes completely, where we are going from from this parameter RT from 0 to 1. At the end of this path, we are selecting only, so this probability is huge of selecting from the first matrix. So this matrix in the middle is very similar to the first one, and even after some rewiring, it is still similar to the first one. And we are benefit a lot from using only the first piece of information. So here, this Reaper 2, okay, the blue color here is doing pretty well. But once again, our method adapts to it. So because it considers two pieces of information, it neglects the piece which turns out to be invalid for the particular situation. And once again, it can adapt. But what is really important is situation in the middle. Okay, here our method just crushes other approaches, and it's much better, because really what happens in the middle is that you have something which is similar to this plot. So you have about half of the entries from the first matrix, half of the entries from the second one. So you have 6 blocks here, six blocks, and Reaper with only one of those 2 matrices cannot have the whole information about the structure of the signal. So that's why it loses with a method which can use both pieces of information simultaneously in the estimation process. Okay, so also with some rewiring lever, we can see the similar situation. We are not winning here so much as before, but still the Aimer is the best from all of these 3 approaches. Okay. And okay, I have only regarding the real data analysis, I have just have some examples. All of them are coming from the analysis where we have HIV positive subjects, and we wanted to find the association between the structure, between the thickness of the cortex and the progress of the disease. And here we combine 3 methods. We have Aimer here, we have Reach without any additional knowledge, And we have Reaper, which combines rich peer and one information for the whole brain in the form of the adjacency matrix. So for Eimer, we divided the brain into 5 lobes based on the picture I showed previously. And that's why the estimates can, actually the estimation procedure can neglect some parts, as you can see here, which gives you much more flexible procedure. Okay, because previously, for example, for Reach or for Reaper, you are kind of forced to use the whole network information, and this may result. So maybe this information is important only for the sum of the lobes. Okay, but you have to use either all of it or none of it. Okay, none of the information. So you cannot any options here. So at the end, oh yeah. So I got the question that y-axis is very different scale. Yes, exactly. This is what I wanted to say. That since suppose that the signal is only in one of the lobe, okay, return zeros. It's not exactly zeros, but it's something very close to zeros. Okay, it's something. So it's MS Peer generally doesn't return any zeros. It's not like a lasso. It's more like a reach. But it's some of them might be very small. Okay. Yes. Not so different. I mean, they are not so different between Reach and Reaper, but Eimer has a different scale. But this is something I just wanted to comment. This is important. This is important, and actually we like that. We observe something like that because suppose that suppose that only one lobe is response relevant. Okay, so the part of B vector corresponding to the frontal lobe of the brain, for example, is truly non-zero. What can you do when you have Reach or Reaper? You cannot by using this identity matrix or by using the 166 by 66 adjacency matrix, you cannot split it. You cannot just you cannot shrink some part of the estimated signal to zero while focusing on the other part. Okay, you can do the average. You can estimate them, but in the average sense. So maybe some of the coefficients are maybe you don't have because you don't have any option. Okay, so you cannot estimate large magnitudes to the frontal lobe because everything is tied together. So those magnitudes are also shrunk because for other lobes the information, the association is not so strong. So you have like the average situation here, and that's why the general magnitude of your estimated signal is much smaller than, for example, for Eimer, which has a chance to put a very small coefficient for some lobes, okay, by putting large penalty corresponding to this part of the adjacency matrix, and then you can estimate much larger magnitudes in the parts of the brain where the signal is really stronger. Okay, you can focus on the important lobes. You can focus on the important lobes, and you can constrain your estimation to those important lobes where the signal is truly observed. Okay, and something like that happens for the different response variable. We considered a few of them. Yeah, Gosia just asked the question, seems a nice way for a group selection. Yeah, I had few ideas regarding that, yeah, your questions. And yeah, this really seems like a nice way of thinking about the group selection. We can actually, I was thinking about combining this even with a lasso penalty. So you can think about such a linear combination of graph penalties and plus the lambda times L1 norm on the vector B. So this would really kill some part of the signal, and this would select the groups of the signal, of the coefficients. Yeah. Okay, so yeah, we observed that for a different response variable, and really you can see the nice behavior in the context of it's really Aimer can put a different ways to the different part of the brains. It's much more flexible than other criteria here. For example, Rich very often is very similar to Reaper, and the estimates from Rich and the Reaper. And Aimer may be much different. And when it's different, then very often the magnitudes of the estimated signal are much larger than for the other. So you can think that this is the way of thinking we have, that the Rich and the Reaper is using very tight, I mean, it's the information which might be maybe too dense, okay, and all of the coefficients are tight together, and Aimer gives you flexibility to just zeroing some of the part of your vector. Okay, and that's it. This is everything I prepared for today. So thank you very much. And if you have any questions, I will try to answer.